Why train? Wheels aren't flat, no steering wheel, no differential, no computer. And yet, this machine, hundreds of tons of steel, traveling at nearly 200 miles per hour, rounds a curve with millimeter precision. How is that even possible? The answer is hidden in a detail that has been carrying you for 200 years, and you've never noticed it. Train wheels are not actually flat. And that one small difference is one of the quiet architects of modern civilization. Set up the problem. You turn the wheel to the left. What happens? The outer wheel, the right one, traces a larger arc. It travels a longer path. The inner wheel, the left one, traces a smaller arc. It travels a shorter path. That difference might seem minor, but in a standard curve, the outer wheel can travel 3 to 6 feet more than the inner one. If both wheels spun at exactly the same speed, the car would resist turning. It would scrub. It would skid. The mechanism that solves this, the differential. That little box in the rear axle allows each wheel to rotate independently at its own speed. Now let's look at a train. Train wheels have no differential. The left and right wheels are bolted rigid to the same axle. One spins, the other must spin at exactly the same rate. No exceptions. So here's the question. In a curve, the outer wheel needs to travel farther, but both wheels are locked together. How can the train possibly navigate that curve without slipping, skidding, or flying off the rails? Engineers at the dawn of the 19th century asked this exact question, and the answer they found is one of the most elegant solutions in the history of engineering. The reveal. At first glance, it looks like a cylinder, but it isn't. Train wheels are slightly conical, meaning the rolling surface is not flat, but gently tapered. Technically speaking, the inner side of the wheel, closest to the flange, has a larger diameter. The outer edge has a smaller diameter. The difference is tiny, nearly invisible to the naked eye. On a typical train wheel, the taper angle is only about 1/20th to 40th of a degree. But that barely there slope is what keeps hundreds of tons of train on the rails. The self-centering system. Let's say the train drifts a few millimeters to the left, nudged by a vibration, a slight unevenness in the track, anything. What happens? The left wheel shifts onto the wider part of the cone. Its effective rolling diameter increases. The right wheel shifts toward the narrower part. Its effective diameter decreases. Both wheels are still spinning at the same angular rate. They're on the same axle. But what does it mean when two wheels have different diameters spinning at the same speed? Basic geometry. Circumference, sidage px diameter. The larger left wheel covers more ground per revolution. The smaller right wheel covers less. What does that do? The left side pulls ahead. The train steers itself back to the right, back towards center. The moment the system goes off balance, it corrects itself. Engineers call this conical contact stability. Or more colloquially, wheel set self-steering. No motor, no sensor, no software. Just geometry. Just shape. How curves actually work. In a railway curve, the outer rail is always longer than the inner rail. The distance between the two rails stays fixed. Standard gauge is 4 feet 812 inches, but the outer arc is larger. On a long curve, that difference can add up to dozens of feet. In a car, the differential handles it. In a train, once again, geometry does. When the train enters a curve, the cars lean very slightly outward due to centrifugal force. That lean pushes the outer wheel onto the wider part of the cone and the inner wheel onto the narrower part. The outer wheel rolls on a larger effective diameter. It covers more distance per turn. The inner wheel rolls on a smaller effective diameter. It covers less. And that difference matches almost exactly the difference in length between the two rails. The train rounds the curve as if driven by a perfect invisible hand. This is not coincidence. This is physics, converted into engineering. The truth about the flange. You see that bold metal ridge on the inside edge of every train wheel. It's called the flange. You've probably always assumed that's what keeps the train on the tracks. Wrong. At least, most of the time. Under normal operating conditions, the flange doesn't even touch the rail. There's a small gap between the flange and the rail, just a few millimeters. The flange is a last resort safety net. It only engages when extreme lateral forces occur. The curve is extremely sharp. High crosswinds load the car sideways. Something goes genuinely wrong. When the flange does scrape the rail, that's actually a problem signal. It causes accelerated metal wear, noise, and energy loss. What keeps the train on the rails under normal conditions is the passive balancing system of the conical surface. If the flange is engaged, the main system has already been overwhelmed. What if the wheels were flat? What if train wheels were perfectly cylindrical? Zero taper at all. The train would be unable to stay stable. It would rock continuously from side to side. Physicists call this hunting oscillation. The wheel set literally hunts for a stable center it can never find. Every oscillation slams the flange into the rail. Every impact accelerates metal wear, generates noise, wastes energy, makes passengers miserable. And at some point, the oscillation grows. It becomes uncontrollable. This is exactly what happened in the early 19th century. The first locomotives with straight wheels were plagued with instability and derailment risks. When the taper was introduced, engineers were stunned. Fewer parts, less complexity, less cost, and a dramatically safer, smoother ride. Today's high-speed trains, the TGV, the Shinkansen, the ICE, all reaching speeds above 200 mph, are built entirely on this fundamental geometry. Without the taper, high-speed rail would simply not exist. Historical development England, 1820s. The Industrial Revolution is at full force. George Stephenson and his fellow pioneer engineers faced a serious problem with their first locomotive designs. Trains kept derailing or dragging uncomfortably along the flanges through every curve. Through trial and error, they began adjusting wheel geometry. They introduced a slight taper. The result was dramatic. The train stabilized. But very few people fully understood why it worked. In 1848, Scottish mathematician and engineer W.J.M. Rankine published the first rigorous mathematical analysis of the conical wheel system, putting the theory on solid ground for the first time. Over the next 150 years, the geometry was refined. The taper angle was optimized for different speed ranges. Rail profiles were engineered to match wheel profiles precisely. New steel alloys were developed for high-speed contact loads. But the core idea never changed. A wheel shaped by a workshop engineer's hands 200 years ago is still spinning, right now, beneath a TGV crossing France at 186 miles per hour. Modern applications and nuances. The bogie system, the rotating undercarriages beneath each car, called bogies, carry all the wheel axles and can pivot independently. This allows long passenger cars to smoothly navigate tight curves that a rigid frame never could. Wheel profile maintenance. Worn wheels are regularly reprofiled on a wheel lathe. The conical surface is restored to its correct shape, because a degraded profile leads directly to hunting oscillation and danger. Rail operators like SNCF in France and JR Central in Japan subject every wheel set to profilometric measurement at set mileage intervals. The data tells engineers exactly how worn each wheel is before it becomes a problem. Super elevated curves. On high-speed lines, the outer rail is raised several inches above the inner rail. This is called cant or super elevation. The tilt balances centrifugal force, so passengers feel much less lateral push through curves. The exact cant angle is calculated based on the design speed of trains using that section. All these systems work together as one integrated whole, and underneath every single one of why this design is genius. The first, solve the problem by adding more parts, more mechanisms, more complexity. The second, find a shape so well suited to the problem that the problem effectively solves itself. The train wheel belongs to the second category. It consumes no energy. It requires no electronics. It needs minimal maintenance. There is no software to crash, no circuit to fail, and it has worked for 200 years. Engineers call this passive design, where the geometry of the system maintains balance, not external intervention. The best engineering does the most work with the fewest parts. The train wheel may be the most elegant proof of that principle ever made. Look out the window. Focus on the point where the wheels meet the rails. Down there, working silently and invisibly, is something remarkable. What keeps hundreds of tons of machine perfectly centered on two strips of steel? Not a computer, not a motor, not a sensor. Just a barely visible slope. Sometimes the world runs on the simplest ideas.